Okay, guys, so welcome. I thought I'll just put this little video together, just as an overview of what we started in class in terms of complex numbers. We know how important these numbers are. We see applications in engineering, in physics. Look at that, differential equations, for example, quantum physics, the wave function, and these are just beautiful. And it's an amazing thing that we haven't seen these in school, yet we've spent over a decade at school. But anyway, what I want to do is just a quick summary and overview, just take you through some of the important concepts with some examples, and then basically you'd go on to obviously complete your tutorials and get some sort of deeper insight into this section over here. So hopefully you'll enjoy this video. And yeah, that's a scary video in the corner over there of me in that circle. But let's move on and let's see what we can give you from here. Okay, folks, so here we see something that we may have, well, definitely would have, sort of encountered at school. X squared plus 4 equals to 0. And then we had to pause for breath because your teacher would have said something like, don't go there. Why is that? Because if you look, you've got something like x squared equals to minus 4. And then if you take the root, you're going to end up with the root of minus 4. Whoa! How do we handle that? Well, we didn't handle that. That was the whole point, isn't it? But now we would tell you that we could easily get there and go plus or minus j times 2. All right. What does that mean? Well, what we're going to say is we're going to get into the complex regime, and we are going to say something like j times j is equal to minus 1, which then means the root of minus 1 equals to j. Now, if you look at some textbooks, instead of saying j or using j, they would use I. So don't get sort of confused with that notation, but here we would use j, and then we're on our way. So we've moved on from let's not go there to let's do indeed explore what lies beyond this real number system. All right, great, excellent. Okay, so let's have a look at this one. X squared minus x plus 3 equals to 0. Now you would remember from school when we were looking at nature of roots, right? Real roots, rational roots, equal roots, and then we went something along the way and said, when delta is less than 0, we looked at what we call imaginary roots. And for a quadratic, what would that mean? X squared minus x plus 3 equals to 0, right? That would mean that the parabola itself, x squared minus 3x plus 3, right, will not cut the x-axis. Is that right? Yeah. So it will not have x-intercepts. Let's put it that way. So let's have a look at this one and see what we come up with. So it's x squared minus x plus 3. We can quickly write this down using the quadratic formula, and I want to basically look at that quickly. And so that's going to give me x equals to, let's just write this out, minus b plus or minus the square root of b squared minus 4ac all over 2a. Right, and from here we know that b is minus 1, so it's, don't forget, lots of minus signs running all over the place, and then it's that minus 1 squared, and then it's minus 4. A is 1, and what's c? C is positive 3 all over 2a, and you can see where we are running into problems, because that could simplify as 1 plus or minus root of, and if you look here, there's a 1 there, and minus 4 times 3, that's going to give you minus 12 all over. Why am I having an a there? That should actually be 1, so that's 2. So what we're ending up with here are two roots, right, which look something like this. So where can I put this? Right over here. So that's going to be 1 plus or minus the root of minus 11, all over 2. And what did this tell us? Don't go there. But the two roots, and I'm scribbling all over the place, could easily be written as x1 equals to 1 plus, and then we're going to go j root 11 all over 2, and x2 equals to 1 minus j root 11 all over 2. Two roots, complex, there we go, and we're done. Okay, so what you can do is take each of these roots, substitute into the original equation, and check whether that is satisfied. And in fact, that will be an excellent exercise, remembering that j times j is -1. That's pretty cool. Okay, so now we want to look at something called the rectangular representation or form of the complex number. We did this, right? So we're basically going to write this camera, you see, I have a face for radio here. So we're going to go z is equal to, we'll write this as a plus j times b, where a and b are real numbers. All right, that's a b, by the way, there. And so you can see that it consists of what we would call a real part, which is a. So we write this as the real part of z, which is a, and then the imaginary part of z, we know all of this, is b, not j times b. And I think that's an important one. And this is called the rectangular form. You get to see this when we're looking at a sort of geometric representation of the complex number. All right, cool. So now I just spoke about the real and imaginary parts, and they could become a lot more complex. You get that? So for example, if I just said something like z um, is equal to 1 minus j times 3, then we know that the real part of z is going to be 1, and then the imaginary part of z is going to be -3. Okay, so you get that. But we discussed things like 1 over j. So for example, what would be the real and imaginary parts for 1 over j? Yeah, let's have a look at that one while we're here. I'll let you think about this one. Z is equal to 1 over j. What is the real and imaginary part? So write that in the form a plus jb, and then you could work out what is a and what is b. We did this in class. Alrighty, so now again, real and imaginary parts. Okay, let's go with the 1 over j. So z is equal to 1 over j. We said, well, let's multiply that by j over j. So j times 1 at the top becomes j. Be careful, j at the bottom, that becomes -1. So this is nothing more than minus j. In the form a plus jb, right? If you write this in the form a plus jb, just to compare, a plus jb, you clearly can see if you're comparing this that a is 0, which means the imaginary part of the real part of this complex number 1 over j is 0, and then the imaginary part, right, is going to be what? Not j, not minus j, but -1. And there we have it. Okay, simple. Now, we also introduced the concept of the complex conjugate. And what is that? What is the complex conjugate? So we basically go z bar, that's how we remember we said a plus jb for z, so this becomes a minus jb, right? A very interesting, and it also helps us simplify things quite a bit. So z is equal to a minus jb. You would have come across the word conjugate acid-base pairs in chemistry. Remember that? Well, this is something different. Okay, so what if we took the product of these two, z bar? What would that be? So for example, if I just gave you a number z, and that was, let's see, √3 minus j, right? What would be its complex conjugate? Its complex conjugate, without any thought, would be √3 plus j. So you just basically change that sign and you're home. Okay, great. Complex numbers can be added. Yes, so we got two complex numbers, and I think we've already said something like z1 is equal to j. Keep it simple. 1 minus j times 2. What is z1 plus z2? Right, so that's going to be j. Write it out. Minus j times 2. So the real part here, that's just the 1, right? And then you look at the imaginary parts, and if you get the imaginary parts here, right, j minus j2 will just give me minus j. So z1 plus z2 would be 1 minus j. Straightforward, nothing difficult. But if I had to ask you what is the conjugate of z1 plus z2, that'll be 1 plus j. Okay, cool. Subtraction, more or less the same, because we want to go like if you had the number z1 minus z2, that is nothing more than, or even take another one and add that to z3. So this is just going to be z1 plus minus z2 plus z3. Now you can knock yourself out. This is very simple, but okay, for completeness, let's take two numbers. Z1 equals to 2 minus j, and Z2 equals to 3 plus 2j, or j2. And if you want Z1 minus Z2 here guys, you've got to be very careful. You see, the use of brackets is very, very important here. So you got the 2 minus, okay, open up the brackets first, distribute, minus 3 plus j times 2, and then you look here for the real parts. 2 minus 3 is minus 1, minus j, and plus 2j. Will this give me that? And there we have it. Okay, nothing difficult there. So you can add a string of numbers, just like how you have organic molecules that they sort of stretch out long chain-like structures if you did organic chemistry. So you can have a string of complex numbers. You could just add them up. You can subtract them, but just be careful. You got the real parts, you got the imaginary parts, and you got to keep them separate. Okay, cool. All right, let's try something else. Oh, multiplication. So let's just take two numbers, complex numbers, and then we'll multiply them, but keeping in mind that j times j is minus 1. So if you try that, let's see what actually happens. So give me two numbers. Z1 is equal to 1 minus j. Z2 is equal to 2 plus 3j. Do this, don't wait for me. So we want Z1 times Z2. What is that? Write it out. 1 minus j, right, bracket, dot, 2 plus, I keep writing 3j times 3. And if you want, and you want to be really careful, you don't have to do it this way, but if you want to avoid mistakes and silly errors, do it like this. And then that minus j into, it's nothing more than just pure distribution, right? So if I multiply 1 into that, I'll just get 2 plus j3, and here you're going to be very careful. Minus, so that it becomes minus j times 2. But watch, there's that minus sign. Then it's j times j. I'll write it as j times j, and there's the 3. Please watch that last one. Go a step further to j3 minus j2 is just j. Now here minus, but j. I'll write it like this. You don't have to go into that much detail. But minus minus, that becomes plus. So 2 plus 3, that's going to be 5. And that's going to be 5 plus j. And you're home. It's as simple as that. There's nothing difficult there. Okay, great, excellent. Okay, so what about division, right? We handle subtraction, addition, subtraction, multiplication. I'm going through this quickly because we went through this in class. So if you look at division, if you watch the other videos as well, you look at division, but before I get through to the division, I want to have a look at the conjugate, z bar, the product. Okay, so let's just quickly have a look at that. And what are we talking about here? So let's just do that. So if I got a complex number defined as a plus j times b, we did this as well. So z bar, which is a minus jb, please try this. Try to work this out. Z times z bar, and we said that was a squared. Not difference of two squares, that becomes a squared plus b squared. Okay, this is very, very important. So please make sure you understand that. So now I want to simplify. I'm dividing two complex numbers. I've got z1 is 1 plus j, and z2 for good measure is 1 minus j. Just keep it simple, straightforward, nothing difficult. So I want the quotient z1 over z2. So that is 1 plus j all over 1 minus j. Right, guys? Simple, straightforward. Oops, there we go. So I want to write this in rectangular form. and we could ask the question, like, for example, what would be the real part of z1 over z2? Now, you can't just go and cancel the j's there. Oh, my goodness. It's when my soul leaves my body when people do that. So what we do is then we would basically multiply by the conjugate, top and bottom, and I would like also just to put in the brackets. People sort of get things wrong by not putting in brackets. So this would be 1 plus j all over 1 plus j. You see, conjugate. So if you look at the top, it's 1 plus j into 1 plus j. That's 1 plus j all squared. So let's just multiply that out. So it's 1 into 1 plus j. You don't have to do it this way. And what's the bottom? 1 minus j into 1 plus j would be 1 squared plus 1 squared, a squared plus b squared. And then if you look at the top there, let's continue on this side. So that's 1, right? Just be careful there. So if you multiply that out slowly, 1 plus j, and j times j is minus 1, and something beautiful at the bottom, that's 2. But watch, the 1 and minus 1 cancel. J plus j is 2j. 2j over 2 is going to be a beautiful j. And we knew that anyway. And there we have it. All right, so we gave you z bar, showed you how to do that, gave you a bit of division here, just quick recall, and be home. Okay, so let's try something else. What's new? Oh, equivalence, right? What do we mean when we say that two complex numbers are equivalent or the same, right? So for example, if I gave you z, how did that change color? Wow, that's amazing. A plus jb, and I gave you z2 is equal to x plus jy. What do we mean when we say that z1 is equal to z2? So I mean, we would know straight away that we take the real part of 1. So this would basically be that a is equal to b. If you compare the real parts and then the imaginary parts, you can't say that. A is not equal to b. Deliberate mistake, just checking whether you're awake. So that becomes the real parts, and this is what I would like to do. The real parts means a equals to x, and then the imaginary parts would give me b equals to y. Lovely. Here we go. And there we have it. Nothing wrong with that. Okay, so just be very wary and what you do when you compare real, imaginary, boom, put them together, and there you have it. Okay, so I just made this up. So let's just see whether it works out. I don't know. I'm just going to put this out there and see whether we can calculate this. So I created a question. Z1 is equal to, I just wrote this out here, e to the 2 ln x plus j ln y, and then I had z2. Keep it very simple, so I put a 4 plus j2 there, plus j2, and we want to solve for x and y. Okay, so solve for x and y. So now we look at the real part. Nice, nice. E to the ln x, and then you got that must equal to 4, and then if you got the imaginary parts, you got ln y equals to 2. Now ln y equals to 2, we exponentiate and figure y is equal to e squared, right? Everyone's happy with that. Now what about this guy, the real part, e to the 2 ln x, right? Now remember the exponential and the ln, right? What are they? What are the inverse functions? But we're going to write this as e to the ln of x squared equals to 4, and we know that when e meets ln, boom, right? They sort of dissolve. One should not speak like that in mathematics, but they are sort of inverse functions. So when e meets ln, you're going to get x squared equals to 4, and so what is x equal to? X is equal to plus or minus 2. So the question is, if x is equal to plus or minus 2, are both solutions to that equation x equal to 2 and x equal to minus 2? Let's think about that very carefully. That's pretty cool, isn't it? Okay guys, so now what we want, we looked at the rectangular form of a complex number in the form a plus jb. But we would like to also look at a graphical representation of this, and this is where we turn to these Argand diagrams that we are talking about. All right, and for the Argand diagram, we look at the complex plane, so to speak. We have the vertical axis, which is the imaginary axis. So I'll just put the imaginary, and here we'd have the real axis over there. That's actually an R, by the way. Oh gosh. Right. So we want to take a simple number and say something like z equals to 1 plus j. Okay, and we want to represent this on this diagram. So if we take a unit, so in the real part there is 1, so I'll just take 1 unit over there, and the imaginary part there is actually 1. It's just like plotting on the Cartesian xy in the 2D plane. And so that's basically what we have. And so we're going to have a point that sits up here, right? But z equal to 1 plus j. So that's basically going to represent, and you know, sometimes people refer to this as a phasor, right? And then we have that basically arrow, but now the question is the length of it, because we got 1 plus j that also gives an orientation, but what would be the actual length of that line? So we look at that as mod z, and that is nothing more than 1 squared. Now be careful, it's not j times j, but it's the 1 there, so that gives me square root of 2. So the length or magnitude of that phasor is going to be root 2, like this. Okay, and then we have an orientation, we have an angle developing in here, and that is very interesting as well. So for the example, that angle theta, we would know would just be tan of theta is going to be just the imaginary part of z all over the real part of z. In this case, it's just going to be 1 over 1. And so it's going to be telling me that theta is now pi by 4, or what we would call 45 degrees. Now also keep in mind, and I think I stressed this in class, and that is for this, we want theta to lie between pi and minus pi. Okay, theta lies between pi and minus pi, or minus 180 to 180. And so now we have the orientation, we have the length, and we can represent this complex number z, 1 plus j, as what you would see in the Argand diagram right over there. Okay, so that's in the first quadrant. What would happen if we were working in the second quadrant? What would that mean? So let's try this and sort of move around, keeping in mind that the theta that we're talking about lies between minus pi and pi. Okay, so here we go. And so let's try a number z. Again, let's keep it very, very simple. So this is the imaginary part, and this is the real part. So in this part, if we're going to be in the second quadrant, then the real part would be negative and the imaginary part would be positive. So for example, there's the minus 1 there, and remember 1 there, and so we're going to have, there we go, right there. And no prizes for guessing over here. So if you want, say, the magnitude of that, this is going to be the root of minus 1 squared plus 1 squared, not j, so that also becomes root 2. So we know that mod z there is actually root 2. But what about the orientation? Because remember, your angle theta, basically, if you have a look, right, we're heading that way, lies between minus pi and pi. So we in the second quadrant, and so if I go tan, let me just introduce a reference angle. So tan of alpha is just going to be 1, right? 1, a reference angle. So that tells me alpha is going to be pi by 4, which is 45 degrees. That's the first quadrant, just like the previous slide. But we are in the second quadrant. So in the second quadrant, in quadrant 2, so we'd want our angle theta, right? Theta to be pi minus pi by 4, and that becomes 3 pi by 4, and 3 pi by 4 is 135 degrees. So you would find some sort of representation like this. Z is equal to, the magnitude is root 2, right? And then what is this angle? That's called the principal value, or principal, yes, angle. So 3 pi by 4. So it's a very nice shorthand notation of the principal value. So it's root 2, 3 pi by 4. That will give us the representation on the Argand diagram of Z equal to minus 1 plus J. Now, of course, let's get into the third quadrant, and let's just basically see what actually happens there, keeping in mind that theta lies between minus pi and pi. Okay, so here, if this is the imaginary and this is the real, so we want a number minus 1 minus j. Does that make sense? So there's your real part minus 1, there's the imaginary part minus 1, and so now we have, if we want to represent that there. So we know, again, this is nothing more than root 2. You can confirm that, which means the length of that phasor, I'll call it phasor. I'm borrowing some elements from electronics, right? You know, people talk about impedance. We start using complex numbers in circuit analysis, for example. So there we have z equal to root 2. And now the question is the angle, all right? If we take the reference angle, if we just introduce a reference angle, so it's going to be tan of alpha, right, real over imaginary, but that's going to give me 1, so alpha is going to be pi by 4. That's in the first quadrant, that's 45 degrees. But if we had to get into the third quadrant, now watch this, guys, we're going to go this way, right? And we were told that if you want to get into the third quadrant, then it is, in school, if you looked at degrees, it is 180 plus the reference angle, or pi plus pi by 4. But that will take us out of that domain of minus pi to pi. Okay, so what we do then is work the other way, that way. All right, so that's just going to be minus pi plus pi by 4, and so the angle theta that we're looking for here would be minus pi plus pi by 4, and what is that going to be? That's going to be minus 3 pi by 4, and minus 3 pi by 4, you can check that, would actually lie between minus pi and pi. So this complex number z can be represented by its magnitude root 2, and the angle is minus 3 pi by 4, and that's its graphical representation on the Argand diagram. That's quadrant number 3. So now let's work with the fourth quadrant. So now we've been through the entire thing, and so we have an idea, but I'm keeping it simple. What you guys have to do is, and I think it's an important one, is you read the question carefully. Are we working in degrees? Are we working in radians? Right? Make sure your calculator is in the correct mode, either the degree mode or the radian mode. Don't mess that up, please. Okay, so let's just get to this one. So back, and we're going to look at the imaginary part over here, and then we're going to go real part over there. So now we want to work in the fourth quadrant. So again, we'll take a positive and then a negative. Of course, I'm just keeping it simple so you can make an easy comparison. Right? We don't look for nice numbers in reality. In engineering and physics, things cannot just be pi by 4 or 3 pi by 4 or 2 pi by 3. Things can get unpretty. Unpretty is a beautiful word. So if we look at this, the magnitude there would just be root 2, yes? Where is this? That's 1, that's minus 1, and that's what we're heading for, right? We're heading for there, and we know that the length, the magnitude there would be root 2. Now we introduce our reference angle again, as usual, tan of alpha, and that's just going to be 1, right? And so now how do we get to the, so that tells us that alpha is pi by 4, but pi by 4, 45 degrees, is in the first quadrant, but we're sitting in the fourth quadrant. And remember, we got the restriction that theta lies between minus pi and pi. So we're going to go and say, well, let's go this way. And so that's going to tell me that theta is going to be minus pi by 4. And so this guy is going to be z equals to root 2, boom. And its principal value here is minus pi by 4. And we worked all 4 quadrants, and so we can practice our Argand diagrams, but for different and more interesting values of z. So for example, I could ask you to plot on an Argand diagram z equals 2, I don't know, say 2 plus j over 1 plus j3. 1 plus j2 over 1 plus j3. Try that. Let's see what you come up with. And that should be beautiful. I'm not saying it's in quadrant 4. You need to basically play around with the conjugate. look at it in a rectangular form, and let's see what you come up with in terms of the angle theta and its magnitude. Right, so this was just some simple illustrations on how we work around the four quadrants, bearing in mind we have that restriction that theta lies between minus pi and pi. So hopefully this is a bit useful. So what's coming up next would be what we're looking at is the polar form or polar representation of a complex number, and then we'll move on to the exponential form of a complex number, because these, especially the exponential form, that allows us to simplify, to divide and multiply with ease, and I think we can do some really nice algebra there, which is what we're going to do in our second video. So hopefully this is helpful. Please go through it, enjoy it, and yeah, have fun.